This reassessment is on Gauss's and Ampere's law. The question says the electric field is measured over a cylindrical Gaussian surface of radius 5 centimeters and height 15 centimeters. Everywhere on the curved part of the surface, the electric field E1 is found to be constant in magnitude, 550 newtons per coulomb, and point radially outward. On the flat end caps, the field E2 varies in magnitude, but also points radially outward. So first it wants us to find the amount of charge enclosed by the surface, and second, if the source of the field is a long, uniformly charged thin rod, part of which is inside the surface, what is the linear charge density on the long rod, Q over L? So this is a picture of what the cylinder looks like. You can see E2 coming radially outward at the top, and that's also at the bottom. And then on the curved part, E1 coming radially outward. And you can see N hat is parallel to E1 and N hat is perpendicular to E2. So with that being said, on the curved portion, E1, like I said, is parallel to N hat. So doing that, the magnitude is just E1. So we can find the magnetic flux. The electric flux, E1 times 2 pi RH, and just plug in the numbers there, and we get 25.9 voltmeters. So on the flat top, like I said before, E2 is perpendicular to N hat, so that means that the flux is going to be 0 when you multiply those together, and that goes for the same for the bottom. So when we do the summation over the whole surface, E dot N hat times dA, we already know that we're just going to have 25.9 because the curved portion is the only thing that has a flux. The top and the bottom has a flux of 0. So using the Gauss's law here, we can rearrange it to solve for Q and plug in the flux that we found here, and this is just the constant epsilon naught, and we get this for the charge that's enclosed in the surface. So for part B, we just do Q divided by L, and we just found that Q, and we divide that by L, the length of the cylinder, and we get 1.53 times 10 to the negative 9 coulombs per meter.